Okay, well, it's my huge pleasure to introduce Julie. She works at the US National Renewable Energy Laboratory, which sounds critically important given the energy crisis we face. But she's got a background in numerical optimization, particularly black box. Nico and Andres and I have been reading her work for a while, and Nico's recent PhD, of course, was related to it, and Julie was very kindly an examiner, which was wonderful. So she's got a bit of an understanding of what we do here in Optima through that, and we're all about to learn a little bit more about the great work that she's been doing. So I'll hand over to you, Julie, and I think I can stay for the whole hour. I've already keyed up Nico. If I have to disappear, he's going to field questions for you at the end in a very egalitarian way, making sure we're seeing all the hands that are raised and everyone has an opportunity to ask some questions. But with any luck, I can stay. Over to you, Julie. Thanks.
Cool. All right. Thank you very much for the introduction, and thank you for the invitation to let me speak here. So I prepared a little bit of talk that's more maybe like a high-level view of black box derivative-free optimization, how we can use surrogate models and active learning to solve these types of problems. If details are required on any of these little subtopics that come up along the way, I'm more than happy to discuss that as well. But to get started, maybe I just wanted to provide one quick slide about what actually is the US Department of Energy. Maybe not everybody might be familiar with it. So the Department of Energy has 17 national labs across the country in the US. These national labs, some of them host very unique instruments and facilities that people from all over the world can use. And all the research at the national labs is very multidisciplinary. So there's a lot of people from different research backgrounds, domain science expertises that come together to solve very difficult problems. The national labs are a little bit divided into, let's say, 3 categories. There's the Office of Science laboratories that focus very much on fundamental research. There's our NNSA laboratories that focus more on our defense mission. And then there's this category of other national labs that are national labs that have a specific purpose, like the National Renewable Energy Lab would focus on renewable energy and energy efficiency. And in my past, I have worked at 2 national labs. I worked at Lawrence Berkeley for the first part of my career, maybe as a researcher, doing a lot of fundamental science type work. And then 2 years ago, I migrated to the Renewable Energy Laboratory with more of an applied focus, where I now have a part a manager, a part a researcher role. In the following, I'll talk a little bit about maybe a difference between Berkeley Lab. So like I said, Berkeley Lab focuses on fundamental sciences. So people there might be interested in cloud simulations. How can we improve them and make them more accurate as they then feed into climate models? And they can then be basically used to give us better predictions about the future climate. Similarly, there's a lot of fundamental science, fundamental research ongoing in understanding ice sheets and how they melt and predicting how they will melt into the future. There is quantum computing research ongoing. There's combustion research where we're trying to understand how gases burn. We're trying to predict that with simulations. There's cosmology research ongoing, again, making huge simulation of how the universe expands and trying to understand the universe. And there's a lot of material science as well. Discovering new materials falls in there. And there's many, 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 many more fundamental science problems that are being studied at laboratories like Berkeley Lab. At NREL, the National Renewable Energy Lab, we focus more on renewable energies and energy efficiencies. Again, we have we have materials discovery, but with a focus on energy materials. We have a lot of work ongoing in wind energy, where we're thinking about designing turbines optimally to maximize power output, to optimize turbine placement so that and steer them optimally so the wakes don't interfere with each other, with the turbines too much, to maximize, again, power output and maybe minimize the probability of losing a turbine in an extreme event. We have a lot of scenario generation ongoing, where we're interested in well, gosh, if a hurricane hits, what's the probability that parts of the power grid go out? And how can we respond by placing emergency assets to help affected communities recover? We have a lot of machine learning modeling, machine learning research ongoing, for example, in climate downscaling. So if we think about climate models, predictions are usually too coarse to be used for renewable energy prediction. We need something on a finer scale, but here we can use machine learning to downscale to obtain, for example, good predictions of wind speeds and wind directions, which can then inform where we build our wind farms. Grid modernization is a big topic as well. There's more demand of electricity, more renewables coming onto the grid. So there's completely new demands on the grid. And we're trying to understand how to basically upgrade the grid to deal with these new demands. And then we also have transportation mobility research ongoing. Maybe you want to optimize the intersections in the city so that the number of people stuck in traffic. And you see the next slide?
Yes.
Okay. Cool. So now I want to talk a little bit more about optimization, because all of these problems that either have been faced at Berkeley Lab or that we're facing at NREL, they're all optimization problems in a different variety of flavors. I guess you all know how to write down an optimization problem, but I like to sort of categorize them a little bit according to what the problem characteristics are. So our objective function f of x here, you can have one of them or multiple. You can have different levels of fidelity of that function value. Objective function may be fast or slow to compute. They may be given analytically or as a black box. Similarly, your constraints, they can just be simple box constraints. They can be linear, nonlinear, analytically provided, black boxes, expensive to compute, or maybe even hidden constraints, meaning you don't know they exist until you try to evaluate your objective function and it fails to evaluate. The parameters can be either continuous integer, mixed integer, categorical, and uncertainty, stochasticity can come in literally at any part of your optimization problem. And depending on which boxes you check in each of these like 4 bubbles here, that sort of like defines, and in my definition anyway, a class of optimization problem that needs a certain type of algorithm developed for it. So for example, if I have a multi-objective optimization problem, then I cannot solve it directly with a single objective optimizer. I have to like do something with the problem to make it so that the solver is able to solve it. Or I could actually develop a new optimization algorithm that directly tackles the multi-objective problem. So the work I've been doing over the last couple of years, so I'm gonna like go over a long development of like research from past years to what we're currently doing, but it all fits all like inside of this black box optimization. So here we're talking about not having access to the description of our objective function and or the constraints even. So I have an optimization problem. I have a big old computer simulation. I stick a parameter set in, parameter set x goes in. I get a function value f of x out. I don't know what happens in between. So I don't have an analytic description of this objective function. That also means that I quite often don't have derivative information available in optimization. We like it to know where the downhill direction is if we're minimizing. Our black box objective functions are quite often multimodal. So there's several local optima present. There's one, maybe multiple global optima. It's all a black box. You don't know how many local optima or global optima there are. Ideally, you find the global optimum, but in a way, until you densely sample the whole space, unless you densely sample the whole space, you will never know if you're actually at the global optimum or not. And then another issue that we encounter is that the objective functions are computationally expensive to evaluate. So each time I want to know what the function value is, I run a simulation, it can take an hour, maybe 2 hours, maybe a day to get one function value out of it. So in a way, I can't afford to do thousands of function evaluations there, meaning I can also not approximate the gradients. So then the question becomes, how can you solve these difficult problems efficiently and effectively? So to that end, surrogate models and active learning have been developed. And maybe if you take anything away from this talk, it's maybe this slide once it's built up. So we start out, we have our optimization problem, this black box simulation, and we know nothing about the function. So what do? Well, initially you have to gather some information. So what you would do is you start out with an initial experimental design. So you sprinkle a couple of points into your optimization search space, and there you do the expensive function evaluations. So here's a little 2D example on the right-hand side. Maybe I decided I wanted to collect initially 4 points for a function evaluations. I do 4 simulations. If each of them takes a day, that means just getting these 4 pieces of information takes me 4 days to get it. So now you can see where the problem comes in. I can not do a lot of these function evaluations. But then the idea is that, well, you have these input outputs, you have the x values, f of x values. Gosh, can't you fit like an approximation model, what we call a surrogate model, to these inputs and outputs? So here we fit a nice little surrogate model. It is accurate in the 4 points where I have function values, and everywhere else in a way it's a best guess of what the true objective function does. But if I was out of compute budget right now, this would be the surface I would work with. I would just rely on its prediction. So everywhere where I haven't sampled, surrogate model makes a prediction and I have to take this as the truth. On the other hand, if I had more function evaluation budget left, I want to exploit the information I get from the surrogate model to decide where to sample in the space next on my hunt for the global optimum. So let's say we evaluated a new point over here in this right-hand corner where this pink arrow is pointing to. So I select a new point there, do an expensive function evaluation. Now I have 5 pieces of information. And since information is sparse, I want to exploit all the information that I have. So what I do is I update my surrogate model. Now it's accurate in 5 points that I know of because I measured there. Everywhere else, again, it's still like a best guess, a prediction. But then I iterate this algorithm. Maybe I have a couple more days for a couple more function evaluations. I select a new point in the space using information from the surrogate model. I get a new input-output pair at this point over here where the pink arrow is. I update my surrogate model. So if you want to take away anything, this is basically it. Information is hard to get to. Use whatever you have. Surrogate models are good approximations of, or best guesses of what's going on across the space. And we need to use the surrogate model in active learning to figure out where are our best options for the next function evaluation. And then we would basically iterate like that until we reach a maximum budget of function evaluations, or we are out of compute time allocation on our supercomputer, for example. So now questions that come up is, first, what is the surrogate model? And what is this suitable acquisition function that tells us where to sample in the space? So I'll talk about some details in the next few slides, and then I'll give some application examples. So surrogate models come in a variety of flavors. In the literature, if you look, there's a lot of papers written where we use radial basis functions. They're nice because they have an analytic description. You can write down the derivatives to get the parameters that are in it. You just solve a linear system of equations. Everything is beautiful. Or another camp maybe of researchers, they like to focus on Gaussian process models. So here's a one-dimensional example where you can see in black, hard to see maybe, in black is the true function I want to find the minimum of. The black dots is where I've sampled the space. The blue curve is my Gaussian process model approximations, or my best guess of what the truth looks like. And the cool thing about Gaussian process models or kriging is that the predictions of the function value, they come with an uncertainty estimate. So in a way, your model tells you how sure or unsure it is about a function value prediction in the space. And you can see this uncertainty is kind of like 0 around where you've sampled, because that's where you have information. So ideally, you know what's going on there. If you have domain expert insights, and you know that your underlying function that you're trying to optimize looks, for example, quadratic, then by all means, you should probably fit a quadratic to the data that you have. So if you have additional information here, that should definitely be exploited when you choose your surrogate model. And now recently, this is not in a data sparse setting, but recently we've seen a lot of growth of autonomous experimentation, of high throughput experimentation, where with one sweep, you can just generate like 200 data points, inputs and outputs. So you find yourself in a large data setting, but it's all in a way black box, not a simulation, but an experiment. And you want to use the surrogate model to still tell what experiments should be carried out. So for these settings, more and more now, we've been using machine learning models or deep learning models to approximate inputs and outputs. So depending on what your problem's characteristics are, how much data you have, how much domain knowledge you have, the surrogate model choice depends on what these problem characteristics are. So this is a little bit some surrogate models here. And next I'll talk a little bit about this. How do we select points, or how do people in the literature select points? So quite often with Gaussian process models, what people like to use is this expected improvement function. They like to maximize it because the goal is you want to select a point that's most likely to improve over the best solution you have sampled so far. So how does it work? We have a one-dimensional example here in this upper image. The red is the true function we want to optimize. The red dots are our sample points. The blue curve is the prediction of the Gaussian process model, and the blue shaded area is the uncertainty estimate. So now what happens is you take the prediction of the surrogate model together with the uncertainty estimate to derive what we call the expected improvement function that's shown at the bottom here. And now you can imagine expected improvement should be 0 at the points where you have already sampled. So that's indicated by these red crosses, because we know what's going on there. We don't expect any improvement there anymore. Everywhere else, this function is larger equal to 0. And now if you were to make the next sample decision, you would say, I want to find the maximum of this expected improvement function. Ideally, you'll be able to find the global maximum of it, but you can see already how this will develop. So as you fill in little crosses down here, as you sample, your expected improvement function becomes increasingly either very bumpy, so you get many optima, local optima, that are hard to overcome when you search for the expected improvement maximum, or you get stuff like on the right-hand side, where the expected improvement is predicted to be 0. So if you started a local optimizer there, you'll kind of like just stop there, not knowing if you're like in a local optimum or have you advanced or anything. So that's maybe a word of caution if you're using Gaussian process models with expected improvement. On the other hand, the other camp, the radial basis function camp, they do not get predictions of the uncertainties together with their function value predictions. They only get like one prediction and that's it. But ideally, when you want to make sample decisions, you want to not only take into account the prediction of the surrogate model, you also want to have some sort of exploration criterion in there. If I was to only go to the minimum of the surrogate model, what quite often happens is you get either like suckered into a local minimum of the surface, or just a stationary point, or even a point that's not even a stationary point, it's just a stationary point on the surface. And then your search gets stuck there. So you're trying to avoid that. So folks who use radial basis functions, they kind of came up with a diversification idea, where here in this two-dimensional example, we have these black dots and this red dot. So I have evaluated my points already. Contour lines is the radial basis function approximation. And now in order to decide where I sample next, they simply go to the best point I've sampled, this red guy over here, and then they add random perturbations to it. And they create a whole cloud of candidate points. And now instead of just using the candidate point with the best predicted function value, they would say, okay, I look at the function value prediction, but I also look at how far each of these candidate points is to already evaluated points. So in a way, if you sample far away from already evaluated points, the idea is that your surface is probably less accurate over there. So adding a point far away from already evaluated points would only improve the accuracy of your surface on a global scale. At the same time, you want to find good predicted solutions. So you kind of like create this score that's trading off the distance of the candidates to already evaluated points and the predicted function value. So those are two different active learning approaches. There are many more out there. Those are just two examples. I'm happy to talk more about other things. Pros and cons. I find personally Gaussian process models work well on smaller dimensional problems when you have a few samples, and also when you have noisy function values, they're pretty good. There has been research recently, though, for making Gaussian processes work for very large data settings. So that's a cool new development underway. Maybe the cons would be that Gaussian process models come with hyperparameters, depending on the kernel that you choose. They require optimization. So you're kind of like solving an optimization problem to fit the Gaussian process model. Maximum likelihood is usually what is used. The expected improvement function, like I just said here, you can see it becomes increasingly multimodal as you add more points. So you get these little blips showing up, or it gets these very flat areas that are not very informative. And solving this expected improvement problem to find the next sample point is in itself already a global optimization problem. Radial basis functions, I find they work well when you have larger dimensional problems, like up to 200 or something, 250 dimensions, I think I've seen in the literature. They work well when you have a large number of samples, and they're computationally quicker than Gaussian process models, because to fit them, all you do is solve a linear system of equations. However, if you're encountering noisy functions, then they don't work so well, I find. Okay, so again, what you choose in your surrogate modeling algorithm for the surrogate model and the acquisition function, it must, in a way, match your optimization problem. And the sampling strategy should also match your surrogate model. Like, I couldn't use expected improvement off the shelf with radial basis functions, because radial basis functions don't give me an uncertainty estimate. And in the following, I just want to talk a little bit about individual projects where we used surrogate model-based algorithms on a variety of problems with different characteristics. So this one is, so I'll start with work at Berkeley Lab, and then we'll go to work at NREL. So in the past, we worked a little bit on cloud simulations. So cloud simulations are difficult. What people mostly use is parametrizations of clouds to sort of like already speed up the simulation a little bit, so they are approximations. But these parametrizations bring a lot of uncertainty along with them, because depending on how you adjust the parameters, you know, they agree more or less with what a large eddy simulation would give you, for example. So here we had a problem where we were trying to tune the parameters in a parametrization such that the parametrization output would agree with large eddy simulation benchmark data. In a way, you can write it down as like the simplest optimization problem ever, probably. So you have an objective function f of x, minimize this error between parametrization and LES benchmarks. You have 6 parameters you can tune. They're all continuous and they're only bound constraints. There's nothing complicated about the problem, except that the objective function f of x is a black box. And the state-of-the-art approach previously was you simply do a parameter sweep, like a grid search. You divide every dimension into equal intervals, do function evaluation at each grid point, call the best grid point your optimal solution. Now you can see that that won't scale very well with the dimensionality. You tend to oversample areas in the space that we don't actually care about what the function values are, because we know the performance is bad there. But we also undersample interesting spaces where we could say in the end, oh, I wish I had refined the grid over here a little bit. So we came in and literally used a very simple surrogate model algorithm. It did radial basis functions with an adaptive learning, active learning search. And some of the results are shown here on the right-hand side. So how do you have to read this? So there's a couple of analytic figures that came out of this project. And what you want is, you want to match the black line. Again, it's a little bit hard to see here in both of these figures. So this is the large eddy simulation benchmark data that we want to match. The green one that's a little bit off from the black is the default parameter. So this is the thing that they found with their grid search. And you can see it, you know, the shape is pretty good. It doesn't match exactly. But the problem is that even just these small deviations of the default from the benchmark have already big impacts down the line when you use those parameters in your cloud model, and if it is then deployed. And then we applied 2 variations of our surrogate model-based optimizer in red and in blue. And we can see that we're pretty much able to perfectly match the LES profile here on both sides. So that was a pretty cool success story. Very short, like kind of like side quest project. But it was, yeah, straightforward, just to formulate the problem and then solve it. And it improved over the good old grid search significantly. Then I want to talk a little bit about gas phase chemical combustion. And you might notice I'm a little bit hand-wavy about a lot of these applications because I'm not a domain expert in clouds, in combustion, or some of the other things coming down the line. So here we were working again at Berkeley Lab on trying to match simulations to experiments. So here we have experimental data from the laboratory where they measured how gases burn, and we can simulate it on a computer. And now we want to match simulations and observations together by tuning the parameters in the simulation. Now, one of the difficulties here is what we call hidden constraints. It means we have our objective function defined over our whole search space. The whole search space is basically valid. But now and then, when you query the objective function, the simulation, for some parameter combinations, you do not get a function value back. So that's what I'm trying to show you on this right-hand side. You have a two parameter problem. So now the question is not only where's the optimal solution, but also where does this function actually evaluate successfully? And these are, I want to say there's not bugs in the simulations, but if you think, for example, about combustion, you make a simulation, has time step. And what you're trying to do is you're trying to observe when ignition happens. And if you have a certain parameter combination where ignition is just really quick and it happens between 2 of the time steps that you have, you will never basically observe ignition. So your simulation will keep running and running and running. And, you know, in a way, these hidden constraints don't mean my simulation ends faster, but sometimes it can actually take longer because in this example, you would just step over the event that you were fishing for. So what can we do to address that? So here we have to think about that our sampling approaches so far, they may not address this challenge of hidden constraints. Ideally, we want to sample mostly points that evaluate successfully because we want to get this information. But we also, in a way, want to learn where this non-evaluable region is. So what we came up with here is we defined an acquisition problem. So we solve an optimization subproblem where we have defined a evaluability function. It's very simple. It's 1 if the function evaluates successfully and 0 otherwise. And then we just fit a piecewise linear approximation to this g of x. So it is illustrated in this little one-dimensional cartoon here. I have 5 points, 3 of them that not evaluate. They get the value 0. 2 of them evaluate, and everywhere in between is just a linear approximation. So now if I wanted to select the next sample point in the space, what do I want to do? I want to say, find me a point that's predicted to be good by the surrogate model. So the function values that were successful, I use them to fit a surrogate model, S of x over here. And then I say, okay, I want to sample at the minimum of the surrogate model, but I want to sample such that the probability that this point evaluates is larger or equal than some threshold Tn that's defined up here. And this Tn depends on the number of evaluations I've done so far and my function evaluation budget. So that means initially, as I just have a couple of points in the space, this threshold is really low. So I can search globally over the whole area. Sample points, probably hit a lot of them that don't actually evaluate, but it helps us build up this SG of x function here. But as I keep sampling along, this threshold will keep increasing and increasing. So as I near the end of my computational budget, the points that I select have to satisfy this constraint over here, and they are much more likely to be evaluable than the points that I sampled initially, like in iteration 10 or 12, for example. So we could show that this works surprisingly well, and this SG of x function is being updated every time you get a new piece of information, and it gets updated each time either with a 0 or 1. So that worked pretty well. Is an example of how you want to adapt your sampling method to the characteristics of the optimization problem that you're dealing with. Now I want to switch gears a little bit and talk about integers. Again, this work is from years ago, but I think still quite relevant for a lot of applications. So in structural optimization, reliability, redundancy optimization, you find yourself in positions where some parameters have to be integers. In simulations, quite often, if you stick a non-integer value into a space where there needs to be an integer, the simulation will not evaluate. So we can't just assume everything is continuous, solve the continuous problem, and then round or something. It won't work here because the simulation won't evaluate quite often. So what we have to do is that we have to guarantee through our sampling that the integer constraints are satisfied. So again, here's a little cartoon on the left-hand side, so maybe I'll explain it with that. So let's assume parameter 1 has to be an integer. Parameter 2 is continuous. So as I set out with my initial experimental design, all I need to do is make sure that parameter 1 satisfies the integer constraints. Parameter 2 can be anywhere. So you can see that these black dots here that I have evaluated, they're at 0, 1, 2, they're at integer values, but everywhere else they're kind of like living on the continuous axis. Cool. Same thing as before, we just made sure that parameter 1 is integer. Then we would go to our best solution we've sampled so far, this red guy over here. And we can do a very similar thing with generating the candidate points as we did earlier by perturbation. But now all we need to make sure is that we perturb parameter 1 in integer increments. So you can see, again, the candidate points, they also like live along these integer lines. So parameter 1 candidate points satisfy the integer constraints. And then in parameter 2 direction, we can perturb them wherever we want them. So now we have little clouds of candidate points, and we can just use the same procedure as before. We look at the predicted function value and the distance of the points to already evaluated points to create a score and select the best candidate point for evaluation. And maybe one word here, if that's of interest. So the radial basis function itself doesn't care that the function has integers. It will just interpolate over everything, even though the function values aren't really valid in between the integers. So in a way, you can fit a surrogate model to everything if you wanted to. So where does this show up? We had a really cool material science problem that we were thinking about. So here we are talking about nanomaterials. We have a substrate. You bake some layers of materials on top of it, and then you're interested in how thick are these individual layers here, and how thick are these layers, the layers where basically two materials meet with each other's. And you can try and determine that by experimentation and compare it with simulation. So in an experiment, you take your sample, put it in an X-ray, and you start rocking the sample to take measurements, and you get observations as is shown in this figure B over here with these dots as what we call rocking curves. And now you can do a simulation where you say, okay, this layer has to be that, and that layer is that, and whatever. Run your simulation, and ideally, you simulated output, the graphs, they match the observations pretty closely. State of the art previously was you have this kind of an Excel spreadsheet interface to MATLAB, where there's a scientist who puts in the different thicknesses of these different layers. They would click a button, they wait a little bit, and then they look at the results, compare them maybe by eye, simulation to observation. Yeah, no, I don't like it. Back to the drawing board, put more numbers in the spreadsheet, click the button, and so on and so forth. So it's a little bit of a waste of human time here. So what we did here is we defined the problem as an integer optimization problem. You would say, well, these thicknesses should actually be continuous, but it turns out that they don't really care about anything below 0.5 angstroms because they can't really measure a good difference between those. So we were able to formulate it as a purely integer problem. Therefore, the number of solutions was basically limited. And we solved it with our surrogate modeling algorithm that I just explained in the previous slide. And we were able to find significantly better solutions way quicker than they did by hand tuning. So just as an example, they would have somebody sitting there all summer long for 3 months, putting numbers into the spreadsheet to get results and get to some sort of a good solution, versus this automation. You start it in the evening when you leave work, you come back in the morning and the results are there. So that was really cool. Where else do we have integer problems? On the top of everybody's mind is probably also deep learning models, architecture optimization. Gosh, you have your data. How many layers and nodes and what batch size are you going to use in your deep learning model? You can formulate that as a black box optimization problem if you make some assumptions here. So in a way, it's a bi-level optimization problem. So I have an objective function, u, that depends on my hyperparameters, my architecture, theta. So I would write down my model, and then what I do next is I train a model. I train the model by solving this nested optimization problem over here. I get optimal weights and biases. They come back to the upper level, and now I can determine what the performance of this architecture is. I don't like it, choose a different architecture. Again, train a model, solve a nested optimization problem, and so on and so forth. There's been a lot in the past of people doing trial and error. There has been a lot of grid search, exhaustive search, and then also way more evolved algorithms to try and solve this difficult problem. So here we used this integer optimizer with the surrogate models, the radial basis function surrogate models from earlier to tackle this problem. And then we could show on a groundwater prediction problem that this actually works really well. So in California, yes, I still live in California. I never moved to Colorado. We care about how much water we have or don't have. We either on either end of the extreme, I always feel like. But in order for us to be able to manage groundwater resources, it might be useful to be able to predict what the groundwater availability in the future is. So what we did here is we trained deep learning models, different types, on time series data on precipitation, temperature, stream flow, time of the year, and also historic groundwater levels. And now the idea is that, okay, assuming I know the precipitation in the future and the temperature, can I predict the groundwater levels, the corresponding groundwater levels in the future? And what this graph shows is that, so we optimized our architectures of these different models. We found models that work really well and some that don't work really well. But in the end, we were able to find architectures, deep learning model architectures, that work extremely well for predicting groundwater levels. So here we had data that we trained on from 2010 to 2016. And then 2016 outwards, we know the ground truth. The ground truth is this blue curve that we tried to match. The model didn't know about it. But we tuned the architectures. And with an MLP, you can see that we were able to really closely match what the ground truth actually is. So in a way, given enough information about precipitation and temperature and stream flow, we are able to make pretty good predictions about the groundwater levels into the future. Now you may say, okay, I don't really know what the daily precipitation will be every day over the next 2 years, but this is a really good opportunity for developing scenarios. Like you can develop extreme scenarios, average scenarios, make assumptions of what the precipitation will be, what the temperatures will be, and so on and so forth. And then the machine learning model, just with a click of a button, gives you predictions of how the groundwater will behave into the future. So whatever scenarios you want to run, this can inform groundwater managers of how to best manage their resources, considering what seasonal forecasts are or what the winter forecasts for our precipitation are once they come out. So I thought this was really cool, impactful work as well. And now we're switching gears to go to NREL. So here we're working on bi-fidelity simulation optimization. Yun So, who's recently joined us as a postdoc, he's interested in simulation optimization, meaning that your objective function you evaluate it twice at the same input gives you back 2 different values. So when you want to optimize that type of problem, you need to get a good estimate of the objective function response. Now, if we were to use the law of large numbers, we could say, okay, we have to evaluate the simulation 30 times at each point to get a good estimate and then therefore get to an optimal solution. But if the objective function, if the simulation is really expensive, we just can't afford that. But here we are working on a project where we use multi-fidelity information. So we have a lower fidelity model as well lying around. That's also stochastic. It's computationally cheaper, but it's also less accurate. But there's a little cartoony on the right-hand upper side with a high fidelity model, the blue curve we want to optimize and the stochastic realization of it. And then we have a lower fidelity function and a stochastic realization of it. And now the idea being that, like, gosh, can I somehow use this low fidelity information to figure out where to sample the high fidelity model, but then also find the optimum of the high fidelity model quite quickly. And now you can see that the low fidelity model has its global optimum somewhere down here in the lower left corner. But it has also a local optimum right here where the high fidelity model has its optimum. So in a way, it could be informative to tell us where to sample the high fidelity model as well. So Yunso has been working on an algorithm where he uses trust region methods that will automatically decide where in the space you will sample, which fidelity level simulation you're going to evaluate, and how often you're going to probe it to get a good estimate of the response of the function. So he called this algorithm AstroBFDF. And this works extremely well. So it automatically decides when you can rely on this low fidelity model, or when you should just like go away from it and ignore it. So the performance of it, we ran it on a bunch of benchmark problems, and we compared it to Yerba Reginaldomide. We compared it to the Adam algorithm and also to his previous single fidelity trust region method for simulation optimization. And in blue and orange is AstroBFDF, 2 versions of it. So you would assume that if the low fidelity model is really dirt cheap, you're gonna sample it a lot. Versus if the low fidelity model is more expensive, then maybe you wouldn't use it. So 0.1 up here in this figure means that the low fidelity model is 1/10 of the price of the high fidelity model. And 1 means that the low fidelity model is just as expensive as the high fidelity model. And a really cool, interesting result that came out of here is that, sure, if the low fidelity model is cheaper, you can get quicker convergence and you can find better solutions. But even if the low fidelity model is equally expensive, it can contain really useful information for you for sampling the high fidelity model, as it might be able to quickly lead you to where the optimal solution is. So I thought that was a really cool outcome of the research. And then currently I'm still working with people at Berkeley. So Luca is a postdoc at Berkeley, and here we're working on inverse design using machine learning. So let's say we have an airfoil shown over here, and we have some target pressure coefficients over the whole airfoil that we want to achieve, and we want to find the corresponding optimal geometry of this airfoil. So it's an inverse problem. So right here again, we have high fidelity and low fidelity information. The low fidelity is a little bit of a coarser simulation. So what we came up with here is that we use a lot of the low fidelity information that's very quick to obtain to train a machine learning model. And now we're asking this low fidelity machine learning model to help us shrink the optimization search box. So if the initial box is large, we ask the machine learning model, where is the optimal geometry most likely to be? It shrinks the search space significantly and therefore cuts off a bunch of the edges and makes the optimization problem in a way easier because the search space you have is much lower. And then we use machine learning models in an inverse design framework that ingest the target performance metrics and the smaller boundaries to do iterative optimization and sampling of the high fidelity model to get to our target geometry here. In black again in this image is basically the ground truth, the thing we try to recover in this example. The red curves are realizations of this algorithm. So you can see machine learning enhanced algorithm. We get really close to the ground truth that we try to recover. And in blue is just a regular differential evolution algorithm. It looks pretty good, but you can see the spread of the solutions is way further, and it's not quite as accurate as the one that we got with the machine learning enhancement. Okay, so that's about research projects. I mean, we're running a little bit out of time. I think I have 2 more slides. Just want to guide your attention towards we're trying to put some of these algorithms online for other people to use. That's always sometimes a little bit difficult to do with our funding arrangements. So we have the hyperparameter optimization software that Vincent put online. You can use it for optimizing different types of machine learning models. It works asynchronously in parallel to accelerate the optimization. So it trains several different models either at the same time or makes you a lot of different ensembles at the same time and has this nested parallelism in it to use all the compute that you have available. And I find it's pretty easy to use on your own data and models. Maybe I would caution still from the Gaussian process model. I think there's still somewhere a bug in there. And then lastly, I talked a little bit about all this optimization research that I've done in the past, which by all means is quite old until now. But we're working on like putting everything into a software that you can download and use, because so far it's all been research software that I sort of maintain, but mostly not. So here currently in this BBOpt GitHub repo, you find optimization for continuous variables and mixed integer variables, for work for when you have black box constraints, for multi-objective optimization. In terms of surrogate models, there's radial basis functions in there. Gaussian process models are on the way. And there are different types of active learning methods, so the sampling strategies that you can use. So there's a lot of features still missing, documentation is still on the way, but there's a lot of references in the code to specific papers that explain what the different sampling methods are. So it's still work under development, but we're getting there, hopefully. And with that, I would like to thank you for your attention, and I'm happy to take any questions you may have.